In this video, we'll use science to build our world's climate. Greetings, dungeon makers. I'm Doc. Welcome to Material Components, a channel for analog tabletop connoisseurs. Today, we're taking the next step in our world building process by determining its climate. If you missed the first episode, there's a link. Pause it. Pause this and go watch. I'll wait. Go ahead. Okay, now that everybody's up to speed, I'm going to format this video like the last one, presenting 3 different methods for determining your world's climate. Again, ranging from easy to probably not worth the time, but this is how I think about this stuff. In order to build climates for our world, we have to understand what it is, what determines it, and why do we even need it? Climate refers to the prevailing weather conditions in a particular area, and weather is basically what the atmosphere is doing at any given time, like temperature and barometric pressure and humidity and precipitation and wind and all that good stuff. Knowing the climate of a certain area gives us insight into what is living in that area based on temperature and precipitation. Higher temperature means higher heat, and heat is energy, so the more energy an area has, the more energy the ecosystem can use to grow and live. Higher precipitation means more water, which, again, all living things need. No water, no life, generally speaking. So why do we care what the climate is? Well, once we know what the climate of an area is, we can determine what lives there. The plants that live there will tell us the terrain type, like grassland, desert, or forest. The animals that live there can help us determine what to put on our encounter tables. Polar region? Gotta have polar bears on your encounter table. Those things are nasty. Also, the terrain will help to determine how easy overland movement will be. Not to mention seasonality, agriculture, fishing, all valuable information when we start populating our world. Okay, no more ado.
And so, without further gilding the lily, and with no more ado,
let me give you the easy peasy version.
Easy peasy.
First step is to divide your world into 9 horizontal regions centered on the equator. If your paper is 8.5 inches high, that's about 216 millimeters. Divide that by 9 and you get 24 millimeters. So each region on your page should be about 24 millimeters tall. The zone at the equator is your tropical zone. Going outward from there, we'll have subtropical, temperate, continental, and Arctic zones. The tropical band has high temperature and high precipitation. In this region, you'll have jungles, marshes in low-lying areas. The rest will be grassland. The subtropical region is a dry region with high temperatures. Here we'll find desert, scrub or brushland, and the rest will be grassland. Next is the temperate zone, which is home to broadleaf forests, marshes in low-lying regions, moors, which are areas at higher elevations with poor drainage. Usually we find these in the foothills surrounding mountains. And the rest will be prairies, which is just what we call grasslands in the temperate zone. In the continental region, those oak, maple, and hickory trees make way for pine, aspen, and spruce, which are conifers, the trees that make pine cones. Again, we'll find marshes in lowlands, moors in highlands, and the rest will be grasslands, which are called steppes in this region. Finally, there's not much in the polar band. Here we'll have ice caps and glaciers, with the rest being tundra. Easy. Done. Next, we'll add a layer of complexity and take the wind and ocean currents into consideration. On Earth, we do have some vague climate bands, but the wind and ocean currents play a huge role in the climates. One quick note here. All of the directions I'll be mentioning from here on out are assuming that our planet rotates in the same direction as Earth, with the sun rising in the east and setting in the west. If you want your planet to rotate in the retrograde or opposite direction, just reverse everything. Okay, wind.
Look, it's dancing with me. It's like there's this incredibly benevolent force that wants me to know there's no reason to be afraid. Sometimes there's so much beauty in the world, it makes my heart burst.
it's just some trash blowing in the wind. Do you have any idea how complicated your circulatory system is?
I know you've slept since then, but in science class you learned that hot air rises and cold air sinks. Since the equator is the place on Earth that receives direct rays from the sun, that's where the air is the hottest, so it will rise there. And if we weren't rotating on our axis, that air would travel up into the atmosphere and make its way to the poles, where it would cool down, fall back to ground level, and then make its way back to the equator to get heated and rise once again. But we are rotating on our axis, which causes the Coriolis effect. I'm not going to take the time to fully explain the Coriolis effect. If you want to know more, I'll leave a link downstairs. But basically it comes down to this. The kid in the middle is walking, and the kid on the outside is flying. How is this possible? It's the same merry-go-round. It's spinning at the same speed. The kid on the outside is traveling a much farther distance than the kid in the middle. But that distance is covered at the same time. So the kid flying around the outside has to go a lot faster in order to cover more ground. The same thing happens on Earth, or any spherical planet for that matter. The ground is moving fastest at the equator and slower as we move towards the poles. Now, as air moves toward the equator, the ground is moving underneath it. That's wind. Because of the Coriolis effect, we have 3 rotating wind cells per hemisphere instead of the one I talked about earlier. These cells are called the Hadley cell, the Ferrel cell, and the polar cell. I'll divide each hemisphere into 3 bands to indicate the 3 cells. The Hadley cell is closest to the equator, and as air is heated by the sun, it rises, moves toward the poles at a high altitude, and finally cools enough to fall back to the ground at about 30 degrees north or south. Then it travels toward the equator at ground level. This causes the trade winds, which blow from east to west. I'll indicate those on the map like so. The Ferrel cell starts with that air from the Hadley cell coming back to the ground, but it moves along the ground towards the poles. This causes wind that comes from the west, and they're called the westerlies. Eventually, the air gets heated and rises again at about 60 degrees north or south, and on our map, they look like this. The polar cell has the same rotation as the Hadley cell, and the winds it produces are called the polar easterlies. All of these winds are called the prevailing winds, and they're very important because they either carry warm or cold air or dry or humid air. Now, ocean currents have a big effect on what type of air the wind carries, so we'll have to add those to the map as well. In the northern hemisphere, ocean currents tend to rotate clockwise, and in the southern hemisphere, they rotate counterclockwise. Once they get to about 45 or 50 degrees north or south, they'll curl away from any coastlines in order to cycle back around to where they started. So I'll start with the general ocean currents on the map. Currents that travel away from the equator carry warm water, and currents that travel toward the equator carry cool water. So I'll indicate warm currents with a red pencil and cool currents with a blue. Here I'm just finalizing all of the currents and cleaning everything out. Okay, great. Now let's start adding the terrain types we talked about in the easy version, but this time we'll take our wind and ocean currents into account. The first thing I'm going to add is rain shade. This happens on the back side of mountains. As wind blows towards mountains, it is deflected upward, and as it rises in altitude, it cools, moisture condenses, and we get rain. So the front side or windward side of mountains get a lot of rain. But by the time the air gets to the back side of the mountains, it's dropped all its moisture, so the backside or leeward side is very dry. So I'm going to indicate those areas on the map. Next, we'll add our tropical rainforests. These will be concentrated in the tropics. I've decided my tropics will be from 20 degrees north to 20 degrees south. Earth's is about 23 degrees, so this planet isn't much different. Now, we're looking for areas with the wind coming from the ocean onto land, carrying warm, moist air. Those regions will have the most rain, and therefore, tropical rainforests. Now we'll fill out our tropics with grassland. Keep in mind that coastlines are usually moist regions, so they may have vegetation where it may otherwise not be. Okay, let's fill out our dry region. Remember, this is centered around 30 degrees north and south because that's where cool, dry air is returning to ground level in the Hadley and Ferrell wind cells. This creates a band of high pressure and dry air, which makes desert the prominent terrain type of this region, which I'll add now. Here's a little band of grassland on the windward side of this mountain range. And here I'm extending this rain shade region into a big desert. Now I'm adding some grasslands in the region that wouldn't be dry enough for deserts because the wind is bringing moist air into those regions. Now we'll move to the temperate zones, looking for the regions that will get the most rain so we can place our broadleaf forests. We'll fill the rest of the temperate zone out with prairie. Moving further toward the poles, we'll now add our coniferous forests to the wet areas of our continental zone, filling out the rest with grassland. And up in the polar regions, we'll have tundra, which I'm indicating with purple, and ice, which is blue. Done. All right, let's go big brain.
Check out the big brain on Brad. You're a smart motherfucker, that's right.
This is the Köppen climate classification system, a set of 5 main climate groups and broken down into 30 climates. Now, we aren't going to get that specific because many of them are extremely similar or found in very small, very specific areas. So we're only going to break ours down into 14 climates. But in order to do that, we're going to have to introduce seasons, which gives us multiple opportunities to world build even beyond climate. The first step is to get the ocean currents mapped out. We'll go about this in the same way that we did earlier in the video, but we're going to start with the equatorial countercurrent, which we left out last time. It's just a current that runs in the direction of the planet rotation, right along the equator. From there, we'll work outward from the equator until we have something like this. Now, I'm going to look outside the tropics to see if there are any coastal regions that might have their climates affected by the ocean currents. Typically, for this to happen, the coastal regions have water carried to it from very far away, and will either be much warmer or much cooler than would normally be there. I'm marking all of the coastal regions that might be warmer than usual in red, and those that might be cooler in blue. Next, we're going to figure out what the wind is doing on our planet. But remember how I said the hottest air rises, and that's the air that is receiving the most direct rays from the sun? Well, that's only at the equator twice a year. During the summer solstice, it's at its northernmost point, and during the winter solstice, it's at its southernmost point. Those latitudes make up the tropics. So from here on out, we're going to have a map for the summer solstice and one for the winter solstice. Yeah, I made a lot of copies of this map.
The Tomster, making copies, Mr. Tom.
Now it turns out that the hottest part of the planet isn't just a flat line. Since land and water heat up and cool off at different rates, the hottest latitudes differ if they're over land or ocean. This is what we call the thermal equator. It's the hottest latitude at any given place around the planet. The thermal equator is important because the Intertropical Convergence Zone, or ITCZ, follows along the thermal equator. The ITCZ is the place where winds converge and rise in altitude. All of the other winds on our planet will be driven by this zone, so that's why it's so important to find it on our planet first. The way to do this is to find the thermal equator. To do this, we have to do a quick hand wave of what the temperatures of our planet are at each solstice. Now, because the Köppen classifications rely on specific temperatures, I'll use those temperatures to create temperature bands around the planet, starting with a very hot zone at each tropic and moving outward to hot, warm, mild, cold, very cold, and extremely cold. The temperature cutoffs between these zones will be the important ones according to Köppen. Since there will be 13 zones and 180 degrees to work with from the North Pole to the South Pole, these zones will be about 14 degrees of latitude each. Now, the thermal equator will want to follow these thermal bands over land, but because of the ocean currents, the hottest part of the ocean is usually still around the equator. So when we map our intertropical convergence zone, it will want to move towards the hottest land masses when over land, but it will want to move back to the equator when it's over the ocean. So in the summer, that'll look something like this, and in the winter, like this. Now, around 30 degrees north or south, you have cool, dry air sinking back down to ground level, causing high pressure areas. But remember, land and ocean heat at different rates, so instead of a band of high pressure around the planet at those latitudes, we get pockets of high pressure. These subtropical highs will form on the west coasts of continents where the ocean currents are moving cool water toward the equator. This cools the air above it, causing it to sink, which makes a high pressure zone. In the hemisphere where it's summer, those high pressure zones will typically hang out at higher latitudes, like 35 or 40 degrees, while in the winter they'll migrate farther toward the equator, like 25 or 20. So let's add our subtropical highs in the summer and the winter. Now, if we remember, land changes temperature much more than oceans, so in the wintertime, inland continental areas are really cold, which causes their own high pressure zones. So let's add high pressure zones to our big continental regions in the winter hemisphere. The wind around these high pressure zones circulate clockwise in the northern hemisphere counterclockwise in the southern hemisphere. Now, starting around our 30-degree north and south lines, we'll draw our trade winds that meet up at the ITCZ. But because of the Coriolis effect, if any of these trade winds cross the equator, they will change directions quite rapidly from an easterly to a westerly. Now, in the poleward regions, we'll kind of go with the flow around these high pressure zones, understanding that winds will generally travel from east or west rather than north or south. Now, we'll draw in some fronts where winds from two different directions meet up. I'm going to add some regions of upwelling where the winds are moving parallel to a continent. Upwelling is when the wind causes a surface current that moves surface water away from an area, causing deeper water to move toward the surface, bringing cool, nutrient-rich water to replace it. You'll have great fishing in these coastal regions, as well as fog, but no coral reef development. In the northern hemisphere, winds will cause upwelling on the coastlines to the left of them, and in the southern hemisphere, it's the opposite. Okay, finally, we can start figuring out what parts of our world get precipitation. Now, in order to get rain, we'll need warm, moist air that has upward movement. So that moisture can condense and create rain or snow or sleet or dogs or cats.
It's dogs and cats living together, mass hysteria.
The easiest place to start is where we find warm ocean currents. These will provide lots of warm, moist air for the coastal regions near them, so they will probably have precipitation associated with that air. I'll mark these coasts in the summer like so, and the winter like so. Now, I'll mark these coastal regions in blue, signifying that they are wet regions, and they'll carry those wet regions downwind until they hit some sort of barrier, like mountains or a front or the ITCZ. If it doesn't hit a barrier, we'll just bring it inland a little ways and assume the atmosphere has dropped all of its moisture by that point. Next, we'll look at the ITCZ. There is a lot of warm, moist air rising in altitude here. So, as you can imagine, there's a lot of precipitation associated with the ITCZ. So we'll take a look at the areas near the ITCZ for optimal conditions. Basically anywhere within 10 to 15 degrees of it. Now, subtropical highs are not optimal for precipitation, so we'll stay away from those. Any areas that are already blue here become dark blue, and we'll call those regions very wet. We're also going to repeat our last step here. Any winds carrying air onto land in this area will drop it as precipitation, so let's mark those areas as wet. We'll look for any barriers such as mountains and fronts as we do this as well. Next, we'll look at the fronts. Areas near those fronts will have a lot of precipitation, though we still have to stay away from those subtropical highs. Any wet regions in these areas will become very wet, and again, create wet areas like the previous two steps. And because these fronts are not stable and their locations are variable, we'll extend the wet areas out a little bit. Orographic precipitation is next. This is wind that meets mountains. The front windward side of the mountains will be wet, and the back leeward side will be dry. Again, any wet regions will become very wet. Finally, we'll look at the polar front, which reaches down from the poles to about 40 to 45 degrees in the summer hemisphere and 25 to 30 in the winter hemisphere. Again, avoiding those subtropical highs. Any coastal regions in these areas will receive precipitation, which will move farther inland the more the winds blow inland. Now, any regions we haven't colored yet will be considered dry. I'll color these regions with yellow. So our final precipitation maps look like this for the summer solstice and like this for the winter solstice. Now we have to figure out what our temperatures are doing. We'll start with the temperature maps we already made and adjust them based on local environmental factors. There are many variables when it comes to temperature variation, but here's what we'll focus on for our purposes. We already covered one, which is the distance from the equator, or at least distance from direct rays of sun. That's what our initial temperature maps reflect. Direct sunlight produces high temperatures and indirect sunlight produces low temperatures. We also see altitude influence temperature. As you get higher, temperature decreases. So at sea level, we have high temperatures compared to high elevations creating lower temperatures. Also, oceans tend to moderate temperatures, while inland on continents, we find more extreme temperature variations. With all that in mind, let's start adjusting our maps. We'll start with the coastlines. Because oceans moderate temperatures, we'll move all of the coastal regions one step towards warm or mild, whichever is closer. So if a coastal region is hot, we'll move it towards warm, and if it's cold, we'll move it towards mild. So here's summer before and after, and winter before and after. Next, rainfall also moderates temperatures. So we'll use our precipitation map to adjust wet and very wet areas one step towards warm or mild accordingly. On the summer solstice, that took this to this, and on the winter solstice, we went from this to this. On our ocean currents map, we circled some regions that are affected by warm and cool currents. Let's adjust our temperature maps for those areas next. Again, moving towards mild or warm. In the summer, that takes us from this to this. And the winter, we go from this to this. Okay, next is altitude. What we'll do here is take anything from 1,000 meters to 3,000 meters colder by 1 step. In the summer, that looks like this, and the winter, like this. Anything from 3,000 to 5,000 meters will move colder by 2 steps. Summer, that's this, and winter, this. And anything above 5,000 meters will be colder by 3 steps. Summer, winter. We mentioned how coastal regions tend to have more moderate temperatures, and the opposite is true about inland regions. So we'll identify our inland regions and take the temperatures 1 step more extreme. So if we have a hot inland region, we'll move it to very hot if it's in the summer, and if it's cold in the winter, we'll move it to very cold. The summer solstice, that takes us from this to this, and in the winter, from this to this. Finally.
Christ, it's about time!
It's about bloody time. I have waited a long time for this moment.
Get on with it.
Yes, get on with it!
It's showtime.
We have all of the data we need to determine our climate zones. Just for review, here's our summer precipitation map, our summer temperature map, our winter precipitation map, and our winter temperature map. Let's begin with our polar regions since they're the easiest. First, we'll map out our ice caps. Köppen says these are regions that never exceed 0 degrees Celsius. So we'll look at our temperature map, and any regions that are below 0 on both maps will be ice caps, which are here. Tundra regions don't exceed 10 degrees Celsius in their warmest month, and on our map, that looks like this. Next, let's map our arid regions. There are 4 arid climates that we'll map: deserts, both hot and cold, and steppe, which is considered a semi-arid climate, also hot or cold. So first thing we'll do is identify regions that are dry in both seasons. Around the edges of these areas, we'll find steppe, and in the middle will be desert. If any temperatures dip below 0 degrees Celsius during the year, we'll consider those cold desert or cold steppe. So here's what our arid climates look like. Alright, let's head back towards the poles and determine our continental zones. Now, Köppen has a whole slew of these, but for our purposes, we're only going to map 2: humid continental and subarctic. Continental climates have a temperature above 10 degrees Celsius in the summer, and their coldest month will be below 0. And basically, all I did to differentiate the two in my map was to make the areas with the coldest winters subarctic. Here's what that looks like. Next, we'll take a look at our temperate zones. Again, Köppen has a silly amount of climates within this temperature group, but we'll be reducing them down to Mediterranean, humid, and oceanic. Temperate climates have an average temperature above 0, but below 18 degrees Celsius in their coldest month. Out of those areas, the regions that are dry in the summer, but wet or very wet in the winter, will be Mediterranean climates, like so. Of the remaining areas, the ones that have hot summers will be humid subtropical climates, like so, and the cool summer regions will be oceanic climates, like so. Now, the reason we left the tropical region for last is because it's the trickiest, but we're so close.
I can almost taste it.
Gross. The tropical region is broken down into 3 climates: tropical rainforest, tropical monsoon, and tropical savanna. We'll start off with the easy one. Any areas that are very wet in both seasons will be tropical rainforest, like so. Next, areas that are wet in both seasons are monsoon climates, like so. And any regions that are wet in one season and dry in the other are savanna climates, like so. Okay, but we still have some regions that we haven't filled in because they didn't fall into one of those categories. Some regions are very wet in one season, but only wet in the other. These will be rainforest near the equator, but will transition to monsoon out toward the arid zones or near the edges of the tropical band. On our map, those regions work out to look like this. The other set of regions are very wet in one season and dry in the other. These will be monsoon climates near the coasts, on the windward side of mountains, and next to rainforests, while they will be savanna climates near arid zones and farther inland, like so. The sequence in the tropical climates should go from rainforest to monsoon to savanna to arid zones, which brings us to our final step, touch-up. Any tropical regions that didn't have the proper sequence, we can fix those now. Also, I have some areas left uncolored because when I mapped out my arid regions, I stayed well away from wet areas. Now, the interesting thing about my unmapped regions is that the ITCZ passes through them as the planet moves from summer to winter and back. So, they will be getting some rainfall as it does. And with those two things in mind, I touched up my map, and here is the final product. Was that a lot of work?
Yup!
Did I enjoy every minute?
Yup!
Hopefully, you enjoyed it as well. As always, I'll leave some reference links downstairs to some amazing world building blogs that go even deeper into this stuff than I do. Next time, we'll break down what we did in this video, and I'll tell you why all this stuff even matters. We may even draw a map. Thanks so much for watching.